So when we've went through and discussed how we can determine if a substitution reaction happens or not, we now know we can use the carbocation type in order to help us figure this out. So we said that in SN2 reactions, primaries will happen greater than secondaries, which will happen greater than tertiaries. And quite honestly, we said tertiaries really don't even react in SN2 at all. So this is one measure that we can use in order to determine the different types of substitution reactions that will happen with the molecules that they provide us in these reactions. Again, those first couple of examples, folks, was just to demonstrate what substitution's all about. And they told us a SN2 reaction will happen. Or they might tell us a SN1 reaction might happen. Okay, that's great. That makes our job a little easier, but sometimes they don't. Sometimes they leave it up to us in order for us to figure this out. All right, so that's one of the ways that we can do that. Look at the alkyl halide, look at that carbon, and what is it attached to. All right, so something else that we can utilize to our advantage here is size. Again, I keep saying it, folks, size matters. So what this means is that if we had a ethyl group with a bromo on it, or a propyl group with a bromo on it, what happens here? I mean, I can't really use primary, secondary, tertiary to make my decision, can I? No. The reason is this is primary and this is primary. Okay, well, what about the branching? In the last example, we saw branching happening closer to the bromo and branching happening later on down the road from bromo. Well, there's no branching in either one of these cases. They're all straight streets all the way through. One street, house on one side, that's it. So I can't really use that as a guideline either in order for me to determine which one of these would happen faster than the others. So there's got to be another reason, and the reason is size. So what we're going to find out is that the larger alkyl groups, so that basically means the propyl or the ethyl, they're going to react slower than smaller ones. Here's how I want you to think about this. Imagine going to a bar, and this couple goes to the bar, and this carbon brings a friend, and that friend brings another friend, and you go as a group. Well, you go into the bar, and there is a nucleophile that's there waiting on a man or a woman. So it's waiting. It sees this couple come in, and it's like, oh, there's the carbon. That's what I've been waiting for all night. Let's see if they'll take me home. But it's going to be a little bit harder for it to go into the propyl bromide because there's some extra carbons that are around that's tagging along. And if you're going to cheat, you don't really want to do it right in front of your friends, do you? And maybe their friends too. Well, compare that over here to the left. This is the carbon that's questionable. This is the one that could be the cheater. This is the relationship that comes into the bar. The nucleophile looks and says, a man or a woman. Okay, so if that goes on, this relationship, carbon has to be sneaky if carbon's going to cheat. So this nucleophile is going to come in, and this carbon has only brought one friend. That's it. It's much easier for carbon to maybe meet this nucleophile maybe outside on the patio, near the bathrooms, near the bar, near the entrance. You know, hey, listen, I've got to go to the bathroom. Could you just sit here with my other and just talk for a minute or two, make them feel comfortable, and I'll be back? Oh, okay. And that's what goes on, and then that carbon runs off, and it begins to cheat with the nucleophile. It's a little bit easier to do that when you don't bring as many people with you to the party. So size matters for that reason. The size of the alkyl groups are going to help us get an idea of how fast or slow this process will happen. So we've already talked about the alkyl halide stability, and now we've talked about branching, because that kind of surrounds the cheater carbon if you're not careful. And now we've talked about the length of just the alkyl group alone that comes to the party or to the club with that possible cheater carbon. All right. Something else that we also want to keep in mind, I think that I've said this already, basically in the summary of the chart that we saw, but we need to talk about the basicities of the groups. So iodine, bromine, chlorine, and fluorine. Fluorine is going to be the strongest base here. Keep in mind, most of the time we've been talking about acids. And iodine is going to be the weakest base, which means this is ugly, and this is not as ugly. Let me put that. Not as ugly. So the ranking of that chart is also going to be very important. So to give you an idea of what this actually translates into, here's a chart that gives you the rates of the reaction. So here, if you look at the alkyl halide, in this case iodide, reacting with a nucleophile, which is OH, this reaction happens, and this is the rate of that reaction, 30,000, folks. Bromide, 1/3, 10,000. Chloride, 200. Look how much slower that slowed down. And then fluoride is going to be the reference of 1, relative rates. So fluoride is going to be the quickest. Or does that mean that fluoride's the slowest? Well, let's think about that for a minute. What does that 1 represent compared to all the other numbers? Does the higher number mean faster or slower? Well, hopefully you can look at this and say, hey, I remember that chart. I remember the ugly chart. And the ugly chart said that iodine is the ugliest. And if iodine's the ugliest, then that means that carbon definitely does not want that toothless, warty little iodine around. So it's got to be kicked off. And any chance that that carbon gets, like with the presence of the OH group, this iodine is going to be kicked off and it's going to go away. This is a very, very fast reaction. It's going to get rid of the toothless, warty iodine every single time that it can do it. Bromine's a little bit prettier, but not so much. Maybe it's still toothless, but not warty. Chlorine, though, out of the Fingerling sisters, again, Saturday Night Live reference, chlorine is a little bit more attractive. So the rate of that reaction slows down. It goes lower. And then fluorine, even more so. And this would be the slowest out of the 4 halogens that we have. So if this lecture is going to involve nothing but alkyl halides, right? That's what we said that was going to be, substitution of the alkyl halides. Then we need to keep this in mind. Iodine reacts the fastest, bromine reacts next, fluorine reacts the worst as far as the speed and the relative rate goes. One more thing that we can think about when we begin to decide an SN2 or an SN1. So I'm going to go back to this chart. This chart you've seen before. There's no differences in this chart versus the previous one. And with this particular chart, again, we are ranking ugliness. But in reality, we're actually ranking pKa's in a way of these molecules, because that really plays a large driving force in what makes a very good leaving group and what makes a good replacement group in order for that leaving group to actually leave. So with that said, here's an example that shows substitution reactions all the way down. And again, how easy substitution should be and is supposed to be. So in this first example, notice that all of our alkyl halides, all the way down, folks, are all the same. They're ethyls with a halogen. A Cl, a Br, an I, a Br, a Cl, a Br, and an I. They didn't really use fluorine because it's very explosive. I'm actually surprised that they even used iodine in here because it is very stubborn, it's very bulky. Chlorine and bromine are typically the go-tos. They're typically cheaper for a lab to use. They're typically a little bit better suited for a lab environment. Shelf stability, a little bit better for them, and so forth. But here we have alkyl halides. And then on this other side, we are reacting it with all of these other groups, right? And most of those groups are going to be located on this chart right here. So one of them was OH. So here's the OH group, right? Way, way below the halogens, which means much more attractive than the halogens. Then we also had SH in one of them, I think. So SH is there. Again, way below the chlorine, the fluorine, the bromine, the iodine. We had an OR group. Okay, well, OR, the R represents any random alkyl group. So the closest thing that's going to be on here to this is going to be here. That's OCH3, not OR, but maybe close enough. We also have an RS group. Well, not really on this chart, but the RS is very much like the RO. So that means a sulfur group that has just an alkyl group on it. So very similar to maybe this one. This one's ethyl group, but R means it can be anything. NH2 group was in that previous example set. That's going to be here, way, way lower than the halogens. An acetylide ion, an alkyne with a negative. That's down here below, way below the halogens again, much prettier. And a nitrile group. Well, there's my C triple bond N. Again, way below the halogens, which is why we focus on substitution of halogens. They're so darn ugly. They're so darn ugly, we don't want them around. So pretty much anything that we bring into the picture will replace them. So the OH comes in, replaces that chlorine goes away, we form an alcohol. The SH group comes in, replaces the Br. Well, that goes on in its spot, and this is called a thiol. Keep that in mind. Alcohol, OH, thiol, SH. They end in the same way. Thio is a word that means sulfur. The OR goes in for the iodine, and we form an ether, ROR. The SH goes into the bromine, and we form a thiol ether. Again, it's not ROR, but RSR, and S means thio in organic. The NH2 goes in, replaces the ugly chlorine, pops out, poop, and we get NH2, which is an amine. And then this one, does this look familiar? Wait a minute. Didn't we see this in the alkyne reactions when we started talking about chain elongation? Yeah, we did. I just didn't tell you that it was substitution at the time. But that's exactly what it is, folks. We have an acetylide ion that was created. We talked about how to create them. We add sodium amide to it. The amide ripped the hydrogen off. We ended up with this alkyne that we called acetylide. That acetylide ion reacted with an alkyl bromide, and this goes on, and poof, off goes the bromine. This is a substitution reaction. That's what we did back in the day. There's no difference here. This is a review. It's a repeat, just in a different point of view. And then down here below, we have this nitrile group that goes in, replaces the I, the C triple bond N goes onto it, and we get a nitrile that happens as a molecule. That's all substitution is. That's all that it should be. Again, though, I'm building this up to the case of SN2 and SN1 because there's a slight difference in the types of products that you get from these. So we have to feel comfortable with the concept of getting rid of the halogen, replacing it with a prettier group first. And then when we see how this works, when we see how this process relates to that chart, when we go through and start talking about, oh, it's an ethyl group, not too many friends are brought to the club, substitution can happen very easy. Oh, well, yeah, this group is a little bulkier, it has some branching. Or, oh, well, this halogen is a tertiary, or this one's a secondary. These things have to take part of the discussion. But we have to be comfortable with the idea of switching these groups out first. Because if we can't do this, we can't do the substitution reactions like they want us to. Now, something else we wrote down that plays a factor in substitution reactions, and that is the solvent. Remember I told you solvent's kind of like the environment. The environment of either 1, are you at the club? Or 2, are you at your parents' house? Or 3, are you at a high-class restaurant? I mean, what type of environment are you in for the substitution to take place? Are you going to be a cheater? Or are you going to end the relationship and then pair up with somebody else before the night's over? And that's our solvent. 2 different types of solvents are going to be used in the world of substitution. The first one is going to be called protic, and the next one is called aprotic. So what is a protic and an aprotic molecule? We need to build our vocabulary. So protic represents basically a solvent, and that solvent has a hydrogen that is bonded to an N or an O. That's it. A nitrogen or an oxygen. Very similar to what we would call a hydrogen bond, right? So, for instance, H2O, right? So here's the water molecule. Hydrogen is bonded to an oxygen. So this would be a protic solvent. An aprotic solvent is, of course, the exact opposite. It is a solvent that does not have a hydrogen bonded to an N or an O. Okay, well, what type of solvent would that be? Well, let's maybe think about toluene. Here's the structure of toluene. That, again, means delocalization in the center. So, do I have a hydrogen that's attached to an N or an O? No, I don't. There's no N or an O in the molecule at all. So this is an aprotic solvent. It's not going to work. All right, well, what about another common solvent that we use in the lab, like ethanol, CH3CH2OH? Is that protic or aprotic? Well, hopefully you're going to look at this and go, ding, ding, ding. Look at there. There's a hydrogen on a N or a O. It is a hydrogen bond. So because of that, this is going to be classified as a protic solvent. That's how we work these. Some aprotic solvents that are kind of common in this world, in this part of organic, they have abbreviations. One is called DMF, and the other one is called DMSO. Let's talk about DMF first. DMF, the D stands for di, the M stands for methyl, and the F stands for formamide. So form is a very common term that's used in organic, and amide is also a very common term used in organic as well. You do not know these yet because we have not talked about them. That's typically a second semester organic course, not a first. So DMF, dimethylformamide, looks like this. The structure of DMF is a nitrogen dimethyl. So 2 methyl groups. There we go. And that nitrogen is attached to a carbon that has a double bond O on it. So this is what we call the amide functional group. Amide, a C double bond O carbonyl with an N. Form means one carbon. And I see that one carbon because that one carbon is the C double bond O. And dimethyl, methyl on top, methyl on the bottom. So there's DMF. If you look at DMF, folks, there is no hydrogen attached to an N or an O. Now, we have N there, and we have O present. But a hydrogen is not attached to either of them. So because of that, this is a aprotic solvent. Now, what about DMSO? Right, well, the D here, what do you think it stands for? Good, di. What do you think the M stands for? Absolutely, that stands for a methyl. What does the S stand for? This is going to stand for sulfur, but we don't write out the entire word sulfur. We just write sulf. And then the O stands for oxide. So dimethyl sulfoxide is a S, double bonded to an O, dimethyl, CH3, and CH3. Some people will write an electron pair here because sulfur is one of these that doesn't necessarily fit the octet. I remember that we told you very early on that it's a little bit of a lie that everything follows octet because it does not. And here we have one of those cases. Notice in this structure we have hydrogen, we have an oxygen, but a hydrogen is not attached to an N or an O. So this by definition is a aprotic solvent. Notice protic and aprotic has nothing to do with polarity. It's different. We're not looking at polarity, right? No time did I see anything about polarity and electron distribution, sharing unequally, and so forth. The only thing that I have said is that H attached to an N or an O, that is protic or aprotic. And this is something that we need to kind of think about in the world of substitution. There's a nice little story about DMSO. To give you an idea of DMSO, this is a very common solvent that's used in the laboratory environment, but people began to put it in creams and stuff as well because it absorbs through the skin. So the story went that there was a woman, she was diagnosed with some type of cancer. She was going through some pain, and she had this balm or this cream that she would order, and she would literally just slather in it all day, every day. And it was helping her pain so she wouldn't hurt. She was very comfortable in the later stages of her life with the cancer that she did have. The DMSO, though, was absorbing into the skin as well as this, quote, painkiller that she was absorbing as well. So DMSO was lathered and lathered and lathered and lathered. And she felt kind of bad one day, enough that she could call the hospital. Something was happening. So 911 was called. The ambulance came to her house, picked her up, took her to the ER. And they took her into the ER. They knew her prior history. They knew some of the problems that were there. She was complaining about pain and so forth. And the story led into her going into the emergency room. So in the emergency room, it was her basically on the bed. And there were a couple of doctors and nurses that were around her during this time. And they were getting ready to basically cut into her. They had to do some type of surgery to see what was going on. So as soon as they began to cut, the nurses and the doctors that were around this table began to pass out. Boom, boom, boom. One after another after another. They don't really know why. It was an odor that was coming from her body. The odor, they believed, was from the DMSO that she just heavily saturated herself in. And by the time they got her to the emergency room, by the time they put anesthesia on her, by the time they kind of prepped her in order for this small type of surgery to happen, they believed that a chemical reaction happened on the inside of her body due to this aprotic solvent. And when they cut her, it actually released a noxious odor gas that came out from her body that was enough to get people to pass out. So they actually had to evacuate the ER area of the hospital and get everyone out of there because they did not have a clue of what was going on. That's a story of an organic solvent, and that's a story of an aprotic organic solvent that you might have, all right? So here's the story and the importance of protic and aprotic solvents. In organic, aprotic solvents are the most common. The reason is because they're more organic, and we're dealing with organic compounds. Protic solvents can be used, though, but they are much less common. And the reason that they're less common, folks, is because these are more polar most of the time. They have hydrogen bonding that they can associate themselves with. And it really is more like an inorganic solvent than anything. Now, I don't want you to get that confused, but protic solvents and organic chemistry typically do not jive very well. I mean, think about the number of times that we've talked about using water as a solvent. There's been very few and far between. So what happens here is that the protic solvent sets this hydrogen bond up. And these hydrogen bonds, the hydrogens that are attached to the N or the O, I'm going to write an F here, but keep in mind that this we really don't see. That's the definition of a hydrogen bond, though, isn't it? An H attached to an NO, or F. Well, this makes for a very polar compound. We see some polarity here. Oxygen's electronegative, nitrogen's electronegative. They're going to suck the electrons up, folks. They're going to suck those electrons up. And what we have is a partial positive and a partial negative. Well, if we throw a nucleophile into this picture, and that nucleophile has this negative that's associated with it, well, yeah, there's a chance that this nucleophile will go onto my halogen, right? That's where I want it to go. There's a chance that that will go on. The problem, though, is that if this is my solvent, solvent means there's a ton of it. So that means that this nucleophile has to work itself through all of that solvent in order to get to this organic molecule. It's going to be very difficult. The reason it has to work itself through the solvent is because it's polar. There's hydrogen bonding involved. That hydrogen bonding is going to interfere. And this nucleophile, when I throw it in, whoop, it's going to be attracted right then and there. It's going to be dumped into a swimming pool of hydrogen bonds. And there's no way that that nucleophile could possibly survive and make it to that alkyl halide. It's in a sea of piranhas, and those piranhas are the hydrogen bonds, and it's just going to nip, 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 and before you know it, there's no nucleophile left. The protic solvents cause us a problem in substitution. So if we use a protic solvent here, folks, if a protic solvent is used, nucleophilicity is reversed. That means the iodine ain't so ugly anymore. So if we throw iodine into a pool of protic solvent and we throw OH into a pool of protic solvent, this is what happens. Both get dumped. The little piranhas are going to be surrounding the I and the OH, and the piranhas are going to gravitate toward the better base, the prettiest one. Here's where pretty doesn't work out for you too well, does it? So this OH is going to get all of the attention, and everything just swamps onto that OH group. It is the prettiest out of the two. That's where the hydrogen bonds are going to associate the best with. What that does is it causes a distraction. And the distraction allows the ugly iodine to escape through, and yay, off it goes. And it leaves that old pretty popular, OH behind. And the iodine can go in and pop, onto the molecule it goes. So very strong nucleophiles get involved with the solvent, and they do not go onto the molecule. And weak nucleophiles are more accessible. They aren't really as held up because they're not as pretty. Those little piranha hydrogen bonds don't want anything to do with them. And they become the nucleophile that we pay attention to in the substitution reaction. So that's where this video is going to stop. Again, we've not done any more examples with substitution. I'm holding off on that just for a couple of reasons. And when we come back, we'll pick up from here and we'll continue our discussion with substitutions and what things play a role and a factor in determining what goes on.